So we could take a look at this next function. Essentially, it's a very similar function, but it's been horizontally shifted down 9. Okay, so it looks like this. And what we want to do is we want to come up with the slope equation for this function. Okay, and we're going to generalize it for some general point x. So I'm going to pick some arbitrary point. We'll call that x here. Okay, so that's going to be point x. This height of this is going to be x squared minus 9. And I'm going to choose some point arbitrarily close to x. We'll call this one point here, x plus h. And then the height of that point is going to be x plus h squared minus 9. And I want to find out the rise and run between those 2 points. And then I'm going to do a limit and make those points come together. So writing this out then with the limit, so I'm going to go limit as the run goes to 0, as those 2 points get closer and closer together. I'm going to do x plus h squared minus 9 minus, okay, so that y coordinate there, x squared minus 9. Okay, so there's my rise. My run is going to be h, and I'm going to do the limit of this. I have 0 over 0, so I need to get rid of that divide by 0. So I'm going to write as limit as h goes to 0. And expand this out, x squared plus 2xh plus h squared minus 9 minus x squared minus 9 all over h. Now, again, like in previous examples, notice that some things just cancel out here. So that vertical shift just cancels out, right? We can just cancel those out. The x squared and x squareds also cancel out. Okay, so the original y coordinate here just essentially cancels out because we don't want that. We just want the difference between those two y coordinates. So we have a little bit of simplification here. So I'm just going to simplify this a little bit more. So as h goes to 0, we're going to end up with 2x h plus h squared over h. Okay, and then we can see that our factor of h will cancel out. And once I take out that factor of h, I can now evaluate my limit. So limit as h goes to 0 of 2x plus h. I can plug it in and I get a slope equation of 2x. So what that tells me is the f prime equation, okay, or the derivative equation, the slope equation for f is going to be 2x. Well, why is that the case? Because I seem to recall the last question, we also ended up with 2x as our slope. But if you think about this problem, this is a parabola. This parabola has the same shape, exact same shape as this parabola. Okay, it's an x squared minus 9. That other one was an x squared. The only difference was a vertical shift. So if I move this graph up and down, the tangent slope at that point is not really going to change at any particular x coordinate because we're just moving it up and down. We're not changing the shape of it. So the slope values at any x point remain the same. So in essence, that minus 9, that vertical shift, really doesn't affect our slope because it's just moving the graph up and down. If I take a graph, make a tangent line here, and if I just move that graph up and down, that tangent slope doesn't change. It just stays exactly where it is. Okay, so we see that result here, and we see it algebraically because those minus 9s actually cancel out pretty much right away. Okay, so let's take a look at the next one here. So this one here has a vertical shift of plus 5. Okay, well, we kind of think that that's probably not going to have any effect on the slope function. But this has a vertical expansion of 3. Well, how will that affect slope? Well, we kind of should think that that is going to affect slope somehow, because let's say we have our graph here, we have our parabola, and looking at the shape of that parabola, if I stretch it, the slope of that's getting steeper. Okay, at all points along there, the slope of that's getting steeper. if I compress it, the slope of those at any x coordinate is going to get less. So steeper, less. So we should really expect a vertical expansion to affect the slope. In fact, that slope is going to affect the rise. That expansion is going to affect the rise, which then should have some effect on slope. So when I sketch this graph, so it's going to be a parabola like that. Okay, I'm going to do my limiting values again. So I'm going to again choose some arbitrary point x. Okay, that point there, the y coordinate there is going to be 3x squared plus 5. Okay, I'm going to find some point close to that x. I'm going to call it x plus h. And that y coordinate is going to be 3x plus h squared plus 5. And we want the slope between those 2 points. Okay, so we want the difference in those 2 y coordinates. And we want the difference in the 2x coordinates, which is always going to be h. Okay, and then we're going to do a limiting value and let that slope go to 0 over 0. So we're going to say that the slope, we'll call f prime, is the f prime function is going to be when we do our limit of rise okay, and again notice that the plus 5's cancel out, so that doesn't really affect our slope. So that's our rise over run. Okay, so we're going to let the limit of that happen. Okay, so I need to make sure I put that as a limit. So f prime of x is equal to the limit as we let h go to 0, or run go to 0. Okay, so if I need to algebraically rearrange this, so I'm going to expand it and simplify it. Okay. So I'm just going to start off by just getting rid of the plus 5s because I can see that the vertical shift of plus 5 really isn't going to affect anything. When I expand this out, I'm going to end up with 3 times x squared plus 2xh plus h squared minus 3x squared all over h. And again, the original xy coordinates tend to cancel out. Okay, we can get rid of that, we can get rid of that, and we can see that now we can generate a factor of h here. So I end up with 3 times 2, so it's going to end up being 6xh plus 3h squared all over h. Those h's now cancel. I can get rid of that divide by 0, and I end up with my slope equation is going to be the limit as h goes to 0 of 6x plus 3h. If I let h go to 0, I'm left with 6x. So there it is. There's a function that calculates the slope values for that graph. Now notice that the slope function is 3 times bigger than this slope function here. So what's going to happen here is that vertical expansion is going to affect the slope by a factor of 3 because we're doing a vertical stretch of 3 times, which is going to make the slope values here and here differ by a factor of 3, which the function also reflects.